Okay. So from the last video, we got to all the rules, and we determined that all that the rules did was that it showed us that to evaluate a limit, we can just plug in the point, the number. And if we have some limit like this, if we have some limit like this, and this is a nasty function, and I don't know trick functions, if we just do all of our rules, this is what it's going to actually look like. I gotta write this nice now. We can take out a constant too, getting this inside, plus the limit of a constant that's all raised to the 1/2 power. This is each term, that's raised to the power, constant out, it's raised to the power. All over, we can separate limits. And there's this one last rule that I did at the very end of the video, but we couldn't get to it. This is the rule. If you have some function, if f is defined on all x, basically, if you plug in any x, you'll get a defined value. If the function has a domain of all numbers, you plug in any number, then the limit as x approaches a of f of g of x equals the limit as x approaches a of g of x. Evaluate. Oh, that kind of looks nasty, but f of the limit as x approaches a of g of x. There you go. F of the limit. If f is defined on all x. Well, what is sine? Sine is defined on all x. Well, you can plug in any number on sine, and you will get a number back. It does not going to be undefined. So what we can do is we can say this is the sine of the limit as x approaches 0 of, wait a second, that's x plus the limit as x approaches 0 of pi. Let's evaluate this using all of our rules that we just did. We plug in that 0, because that's a rule. Okay. Plus twice times 0. Plus 5. Limit of the constant is just that constant. All to the 1/2 power, or square root of that. All over the sine of plugging at 0. Limit of a constant is just that constant, a. That's the limit. I forgot to put the power 2. But what does it look like we're doing? What if I just plug in 0? Well, that's what we're doing here. We are literally plugging in 0. All these rules just prove to us that we just plug in the point. And this would be what? The square root of 5. The sine of pi over 2 is 1. So just square root of 5. Yeah. That was the last section. That was just what all my point was for half an hour. That was what I was trying to tell you. Now, we're ready to tackle on what happens if we have an undefined point. And I kind of gave you a hint on that already. So, if we have a function like, let's see, x squared minus 4, x plus 2, right? And I say evaluate this limit as x approaches 2. Okay. Plug in. You get 0 over 0. Undefined automatically. This is what we call an indeterminate form. Indeterminate form. I don't know if I wrote that right, but it's an indeterminate form. Basically, if you're evaluating a limit, and if you plug in the number, you get 0 over 0, indeterminate. It's indeterminate. Okay. Well, how do we make... But does that make the limit exist or not? If we had a hole, the limit right now exists. It exists at A. And it does give us some limit L. But L does not equal f of A because f of A is not defined at that place. So we have to work with it. We have to do algebraic manipulation to get what we want. And if you remember one example of the first video, I think we did an example kind of like this, but we had it in a factored form. And you can kind of see that we can get rid of the problem and fill in the hole, kind of. And that's how you solve this kind of limit. So for this one, you would say, okay, let's factor it. We get x plus 2, x minus 2. You would notice that these are common factors. And you would say this is the limit as x equals 2 of x plus 2. Now you have to write the limit here, here, and here. You have to write it here. You have to write it always until you plug in the number. As soon as you plug in the number, you can stop writing limit. That's 4. So what we just did is we took an indeterminate form and turned it into something we can plug in. Okay. Kind of easy, right? Then it gets hard. Because now we can get some limits out like this. And now, in the example book for this one. Okay. The first thing you want to do is just plug in the number and see if you can actually get a value out of it, or just an indeterminate form. And if we plug in our number, we get the square root of 5 minus the square root of 5 over 0. Well, actually, it's 0 over 0. Wait, that's an indeterminate form. That means we have to do some algebra to get something out. And the thing that's causing the problem is that x. Because what we're doing is if we let that equal 0, that's going to give us a problem. So somehow we have to get rid of that x. And for this kind of look, you'll see a square root and a minus. If you've ever heard, you probably already know algebraic function. You gotta multiply by the conjugate. And it does something special. It helps you out. The conjugate is x plus 5 plus the square root of 5 over x plus square root of x plus 5 plus square root of 5. The conjugate is just the same terms but with the plus sign. And that gives you different squares that will make your life easier. That will just get rid of the square roots. Do not distribute this one, the denominator. Don't do that. Because you're trying to get rid of the x, you're not trying to mix it up with other terms. So this is the limit as x approaches 0 of, if you know difference of squares, this will become x plus 5 minus 5 over x times this entire stuff. Now notice we're multiplying by 1 because it's the same thing over the same thing. So it doesn't do anything, but it's just an algebraic trick. Wait a second. This is a 0. We still write limit because we're not plugging any other values in. We get x over x times the square root of x plus 5 plus the square root of 5. Oh, we get a common factor. We get our x's and our x's. Oh. That's nice. So we get 1 over the square root of x plus 5 plus the square root of 5. Let's plug it in. Now we stop writing the limit because we're going to plug in 0. And we get 1 over 2 root 5. Now if you want that simplified, you can simplify that, but we usually leave our answers like this. You can write it down like the square root of 5 over 10. You could do it. But you don't have to do it. That is acceptable. That's just more preferable. But it's not that bad in terms of math. Okay. Let's get a different type of question so we can see it. So far, so good. Okay. So this one's a little bit different. have this kind of problem. This one is a complex fraction. You might just say, oh, I give up. I don't want to do this. And all you gotta do is just get rid of the complex fraction. If we plug in 0, let's just plug it in. We get 1/4 minus 1/4 over 0. That's 0 over 0. That's an indeterminate form right there. We gotta get an x up on top somewhere because that's the thing that's causing the problem. It's giving us a 0 over here. So we gotta do some algebra. We gotta get rid of it. All these questions will look similar like this. They won't kind of change. Okay. Well, let's make this one fraction. So if we get common denominators on those fractions, we'll get 4 over 4x plus 4 minus x plus 4 over 4x plus 4. Okay. Let's put those together. If we subtract 4 minus x minus 4, we get that. That'll be minus x minus 4. That'll be 0. If I make a mistake, please let me know. Now make it a simple fraction. Hey, those cancel out. Let's go over here. We got the x's on each side. Now if we plug it in, we get negative 1 over 16. That's our answer. That was an even question. Let's look at that. So for this kind of question, common denominators on both sides. We subtracted. We got negative x over that because the 4's cancel out. We simplify this complex fraction into a simple fraction. Cancel out all common factors. Negative 1 over 4x. Negative 1/16. The algebra isn't that bad. It is not that bad. And there you go. Okay. Let's go to the trig functions. Limits of trig functions. And before we discuss this, we have to discuss a special limit. This one right here. And we have to discuss this one right here. You have to memorize those. They were very special for a couple of reasons. One, they'll just be super special next time. And they help us get more answers. Now, honestly, there's a mathematical proof for these using the squeeze theorem. I personally don't use squeeze theorem. We can just find this out graphically. And using a graphing calculator, you can plot these. There will be a hole, and you can find the limit graphically. This one equals 1, that equals 0. Those are the special ones. You gotta know this one. So let's do some trig ones. Okay. What is the limit as x approaches 5 sine x over x? Remember the limit properties, we can take our constants out. So we can say this is just 5 times the limit as x approaches sine x over x. Wait a second, we know this. That's a 1 right here. 5 times 1 is 5. That's an s, but 5 there, but it looks like an s. That's 5. And you will do this oftentimes in calculus, where you will have to match something you know. So you have to match something you don't know to something you do know. That happens so many times. You have to know all that. Let's do another one. The limit as x approaches 0 sine x this one. Sine x over 5x. Again, the same thing out. You gotta visually see that there is a 1/5 sticking out. That limit is 1. That limit is 1. Just 1/5. 1 times 1. We can pull that out. 1/5. Another example. The limit as x approaches 0 of sine squared x over x. This one's a little bit tougher, but we gotta visually see this. Wait a second. This is just sine x times sine x over x. This limit is going to be 0. This one's going to be 1. So it's 0 times 1. That equals 0. Remember the properties, you can separate limits by multiplication. There's one more Couple more, sorry. But they just kind of rattle the brain. With the trig limits, you gotta just think outside the box. Okay, so, that's a doozy. What do we get? We can't cancel at this time. We get 0, 0 in determinate form. How do we get it to look like this? I'll get closer. Multiply by 1 over x over 1 over x. You gotta see enough examples in order to do some of these. And from here, I'll multiply 5 over 5 times 2 over 2. That's just 1 over 1 over 1 over 1. You get sine of 5x over 5x, sine of 2x over 2x. Wait. That's not that. But we'll let u, just a substitution, equal 5x. Then I get a limit as x approaches 0 of sine u over u, which is just 1. It doesn't matter what the variable. Oh, we could do a little substitution. Give us the same thing. That's a little trick you can use, but this is going to be 1 over 1, which is going to give us 1. I'll do one more before I get to a little bit of a different type of topic, and plus my thing's about to run out. Okay. I'm going to do this one really fast, but it needs a lot of thought. Okay. I see both sides and cosines. I see both of these at the same time. You understand I'm going to pull out that constant out. I don't want that. Also, as an x squared, that's x times x. It's illegal to do this. And if you multiply these, that gets that with the 1/2. You see how that gets to x squared and that gets to that? You multiply those two. Wait, I know that one, I know that one. That one's 0. That one's 1. That's going to be 0, 0. That's entirely 0. That's how you get it. Okay, real quick. Let's do this one. The limit as h approaches 0 of x plus h squared minus x squared over h. Ooh. There's no numbers here. They're just variables. Let h approaches 0. Wait, what happens if we plug in h? Oh, we get an indeterminate form. Because they got x squared minus x squared. Oh, 0 for 0. We have to do some algebraic manipulation. We have no choice but to expand the top. These cancel out, we can factor an h out.